So, welcome to General Relativity Lecture 4 on Lorentz transformations and the Poincare group. So we've previously talked a little bit about Minkowski space, right? And so let me kind of frame this discussion with a parallel discussion. Like, imagine you were just introduced to three-dimensional space, right? XYZ space. And then you had the thought, well, okay, I can use XYZ coordinates, but what other coordinates can I use that, still maintain the character of the space, let's say? And how would you characterize the character, characterize the character of the space? So in Euclidean 3 space, the main thing would be distance, right? So you might wonder what other coordinate systems you could use that would maintain your concept of distance. And the answer you'd be led to there are coordinate systems which are just like rotations of the original coordinate system, and perhaps reflections, and also, of course, translations. In other words, the group of rigid motions. Those would take you to coordinate systems that were related to your original Cartesian coordinate system by like a shift and a rotation, and maybe a reflection. All right. So now we're begging the similar question for Minkowski space. If you start with a, set of coordinates for Minkowski space, namely like x0, x1, x2, x3, then what other coordinate systems are allowed that maintain the, the basic nature of Minkowski space that aren't, So, I mean, really the question then is, what is basic to Minkowski space? And the answer to that question, at least as Carroll approaches it, is that the interval is the basic thing, right? And that's fine. So let's get to it. So here it is. The Poincare group is actually the analog to rigid motions for Minkowski space. These include Lorentz transformations and space-time translations. These translations leave the invariant interval unchanged. So just a definition here. You got your just straight up translation of time and space, space-time translation, and then the analog of a rotation, right? It's called a Lorentz transformation. And Lorentz was a contemporary of Einstein. There's a bunch of people working on this stuff back around the turn of the 20th century. A lot of the equations which we have in special relativity were discovered by other people other than Einstein in an attempt to answer the problems posed by the apparent lack of the luminiferous ether, as demonstrated by the Michelson-Morley experiment. So then those equations, which were just sort of invented by pure necessity by some people, were then later derived in the logical framework of special relativity. And I think some of the things you find, like length contraction and other things, fall in that category. Anyway, I am not 100% sure what I'm telling you, but I just remember vaguely from my reading in special relativity back in the day. Let me move on here before I tell you something that's not true. Now, so if we have event x1 and x2, we can translate those to x1 prime and x2 prime, and then we can look at the increment between those by taking their difference, and it's just the same increment, right? So it's very silly that the invariant interval is maintained for a translation, because even the increment is maintained, right? Even the increment itself is invariant. So of course, the invariant interval, which you calculate from the Minkowski metric acting on the increment in itself, is the same. So, all right, Lorentz transformation, on the other hand, the increment's not invariant. It's sort of in a general sense rotated. So here lambda is a 4x4 matrix in both cases, and here x1 prime and x1 and x2 prime and x2, these are four-dimensional column vectors in my formalism. I work with Rn as column vectors. All right. Anyway, so what we got here? Events x2 and x1 are Lorentz transformed to this and to that. So if you look at the increment, you end up with this 4x4 matrix times the original increment, right? So the transformed increment is the Lorentz transformation of the increment, as it turns out. And so when you look at the invariant interval of the transformed increment, it's this, all right? And so by Sock-Shoes, that gives us increment transpose, Lorentz transfer matrix, Lorentz transformation transpose, matrix, Lorentz transformation, increment again. Okay, fine. This is annoying, but is it the Lorentz transformation lambda, or is lambda the matrix of the Lorentz transformation, right? So there's always this issue with linear algebra. Is the transformation and the matrix, are they the same thing? Well, technically no, but I will at times abuse language and refer to lambda as the Lorentz transformation. You know, admittedly, it is the matrix of the Lorentz transformation. I don't think I even have a notation for the transformation itself, honestly. Anyway, so the thing is, the Lorentz transformation is precisely those such that, as we set up here, right, eta is equal to lambda transpose eta lambda. So that's how we define a Lorentz transformation. Here, eta is that specific matrix, which I just put out a screen here, up here. It's this particular matrix, with a diagonal matrix with -1, 1, 1, 1 down the diagonals. And you know, lambda is a matrix which satisfies this relation right here. That makes it a Lorentz transformation. And if you have that rule, as you can see, it leaves the Lorentz transformed increment invariant. See, so we get this is equal to eta, which we're back again to the Minkowski product of the increment with itself, which of course shows you that delta s prime is delta s squared. In other words, the invariant interval is indeed invariant under a Lorentz transformation, and all is well in the world. So we should have some nice notation here for the set of all matrices which correspond to Lorentz transformations, which I will generally just refer to as Lorentz transformations. So O31, it's 4x4 matrices that solve this equation here. Eta equals to lambda transpose eta lambda. At the level of index notation, it looks like this, which I won't try to verbalize, but you notice there's contractions here over the mu prime and over the nu prime. The sigma and the rho are free. And interesting calculation right below. If you look at, and I seem to have introduced a new character to the story here all of a sudden. My bad. These thetas are the dual basis to the standard basis. So like, I guess I just should write it up here. Rats, I already scanned this thing. I hate to scan it again. Oh man, do I have no? Okay, so like R4, for us would be the span of, you know, let's see, in our current notation, E0, E1, E2, E3, right? And dual vectors to this, theta, we're using a theta in this, in his, other classes, sometimes I'll just use the same letter with an upper index, but I'm trying to use a different letter just to be, well, to introduce yet another notation into my, into my materials, just to be annoying. But anyway, it's the dual basis. In other words, it's defined, theta mu is a mapping from R4 to R, which is defined by, now I haven't been super careful about leaving the indices upstairs matching upstairs, downstairs matching downstairs. I haven't been completely, what's the word, simpatico with like Carol on this point. I sometimes have had lower mu nu for a thing like this, whereas he's more careful to keep the indices matching like that for the most part. There are a few different conventions that you can go with. Anyway, so this serves to define theta mu as a so-called covector or dual vector from R4 to R, all right? So why is that true? Well, just a little bit of linear algebra here. So it suffices, if you're going to define a linear map, right? If you define the values of the linear map on a basis, here E0, E1, E2, E3 is a basis. So I've fixed the values of this mapping on a basis, then you can extend linearly. That defines a unique linear mapping. And these theta upper mu, in other words, theta 0, theta 1, theta 2, and theta 3, we've defined 4 linear mappings. They're so-called dual vectors to the standard basis. And that's what I'm using here. So we can write the Minkowski metric as a sum over the Minkowski matrix and the tensor product of these covectors. All right, now, as sometimes happens here, I'm getting the cart before a horse a bit. I will come back and talk more about tensors a little bit more systematically in a future lecture. My apologies again. All right, so, and I think the future lecture where I talk more systematically about tensors is lecture, I want to say 6. But there will be many lectures where we talk systematically about tensors in this course, so anyway. Alright, so anyway, here we go. The Minkowski metric could be written like this in one of the coordinate systems, right? In the unprimed coordinate system. But if we switch over to a primed coordinate system, right? In other words, a Lorentz transformed coordinate system. In other words, a coordinate system which is related to the original coordinate system by a Lorentz transformation. Alright, enough words. Then when we transform the dual basis, we'll learn that the way that the dual basis transforms is by a Lorentz transformation like so, and like so. So I transform the dual basis according to their rule, and then you're left with this eta lambda lambda, and if you go back up here and move things around just a bit, you'll see that if you just put the eta mu prime first and put these guys second, that's exactly what you have here. So that's exactly equal to eta sigma rho, which I put here, and then you get this. In other words, the components of the Minkowski metric, right? Let me put it in a different way. What this calculation here shows is that if the components of the Minkowski metric, right, are eta mu nu, right, in one coordinate system, then the coordinates, then the matrix, the components of the Minkowski metric in any other Lorentz transformed coordinate system are also eta mu nu. Of course, with the mu prime and the nu prime, but that's just our nomenclature to explain that we're changing from the unprimed to the primed coordinate system. So that's good, because if you had the situation where you changed coordinates and your Minkowski metric changed its formula, that would be kind of disturbing. That would be like in the story I told to start with here. It'd be like if you had Cartesian coordinates and you changed to another allowed coordinate system, and then all of a sudden the formula for like the hypotenuse of a triangle all of a sudden had like a different number in it or something. That'd be really weird, right? We don't want that. Okay, so because the Minkowski metric is, you know, roughly speaking, the analog of like the Pythagorean theorem for Euclidean geometry. It is that sort of truth. Now, anyway, long story short, the matrix of the Minkowski metric is eta with respect to any inertial frame. All right. I would encourage the reader not to think too deeply about what I'm saying. In some sense, I'm showing consistency right now. I haven't been so careful as to lay down an initial definition and derive consequences of that definition. I'm being more physicsy in my presentation at the moment, in the sense that if you ask which came first, the chicken or the egg, you just, I don't know. There's a chicken, there's an egg, and they're related, you know? It's physics. Okay, so I will try to be more systematic as time goes on here, though. All right, so anyway, just a remark, in R3, the matrix of the dot product is the identity matrix. If we use any coordinate system which is rotated from the usual coordinate system, it still works out, right? So like here it is, if you're talking about the dot product for 3 dimensions, then that formula can be V transpose W. If you put an identity, 3 by 3 identity matrix in there like that, you get that. So this is the matrix of the dot product, just like eta is the matrix of the Minkowski product. And here, if we rotated the vectors by a rotation matrix R, then by the usual linear algebra here, sock shoes, we see that we need that the rotation matrix transpose times the rotation matrix has to be the identity. That's the necessary condition in order for the dot product to be invariant under this rotation. And for that reason, we define the rotation matrix to satisfy the condition R transpose R equals to I. So essentially, for the same reason, we define the Lorentz transformation to be the transformations such that eta is equal to lambda transpose eta lambda. And in fact, this is part of a larger theory. If you had a more abstract bilinear transformation on a vector space, you could define the linear transformations which leave it invariant and study the properties of those linear transformations. That's an interesting bit of linear algebra that you can do. I think if you read Roman's Advanced Linear Algebra, he does some of that for a few different kinds of things. But anyway, all right, so anyway, here we go. Here's some special examples of Lorentz transformations that are kind of peculiar. And so one of them is time reversal. So if you do -1, 1, 1, 1, that will satisfy the condition lambda transpose eta lambda equals to, eta again. And so will all these parity transformations. These are spatial inversions. 1 minus 1 1 1, or 1 1 minus 1 1, or 1 1 1 minus 1. You can check it. All of these guys satisfy the equation lambda transpose eta lambda equal to, oh, well, I'm sorry, I'm doing the time reversal here, this calculation. I used lambda sub t for time reversal. And like the time reversal actually is eta itself. That's kind of funny. So you get eta cubed, but the cube of a diagonal matrix is the cube of its diagonals, which gets you back to eta again. And here's the exciting calculation for the spatial inversion on the first coordinate. Again, it solves it. So just like in the study of three-dimensional geometry, you go looking for rotations and you find rotations and reflections. Here I go looking for Lorentz transformations, and I also find these time reversal and parity things. They're there. Sometimes you don't want them to be there. All right. What's possible? Like what can we say more about the structure of the Lorentz Lorentz group? Well, I just said Lorentz group. That kind of says a lot, doesn't it? It is a group. I don't think I've even written that on this notes, but that sounds like an excellent homework problem. Show that the Lorentz group is a group in the sense of mathematics, right? It's closed under inversion and multiplication. It's a subgroup of the general linear group of matrices, of 4x4 real matrices. So of course it's automatically going to be associative, right? The identity's in there. Okay, so anyway, theorem. If you have a Lorentz transformation, its determinant is plus or minus 1. So basically you just take the determinant of the defining condition and use properties of the determinant, and since the determinant of a product is the product of the determinants, and since the determinant of a transpose is the determinant of the matrix transposed, we quickly get to 1 is equal to the determinant of lambda squared. And if that's the case, it must be that the determinant of lambda is plus or minus 1, since it's a real number. So apparently there are two kinds of Lorentz transformations. At least we can bifurcate them into the ones with the determinant 1 and ones with the determinant minus 1. Ones with determinant 1 are known as special orthogonal matrices, the type 3-1. So lambda, a Lorentz transformation such that the determinant's 1. And then for physical reasons, we're often interested in, so I shouldn't tap the floor here, it makes everything vibrate, doesn't it? Whee! Oops. this is the proper orthochronous Lorentz group. And so that's defined to be, this is the connected component of the identity of the Lorentz group. It's the ones with determinant 1 that are also not time reversals. You know, they've got lambda 0 prime 0 greater than or equal to 1. And Carroll has a couple sentences explaining why that's not ludicrous to suppose. But these, oftentimes when we talk about the Lorentz group, we're actually implicitly meaning this, but we won't actually pretty much ever say proper orthochronous Lorentz group, even though that's often what we mean. All right, so just got to be aware of that. People throw out parity and time reversal typically when they're talking about Lorentz group. Now, perhaps they put them back in when they're talking about the full Poincare group, though. Maybe. I don't know. I think to be clear on these ambiguities, you just gotta ask questions, depending on the discussion which is posed. You know, so just be aware of these issues is the main thing. So some examples. Of course, the first example is that because the Minkowski product is like the dot product with minus term for, you know, the time part, if you just do 1 and an ordinary 3-dimensional rotation, well, that's going to work out basically because it's just rotating the spatial part, and we know if we just do a regular old spatial rotation, right? Now, determinant 1 makes sure that you're throwing out spatial inversions. That keeps it just a rotation, not a reflection, you know. But this is going to maintain the Minkowski product. I mean, it's going to satisfy the defining condition for the Lorentz matrix, because lambda transpose eta lambda is going to be this. But since R is a rotation matrix, R transpose R is I3 again. And there we go. So, and you can also check that the determinant of a block matrix is the product of the determinants of the blocks, if it's block diagonal. If it's not block diagonal, then things are known. If you want to look them up in Gullub's, is it Gullub? It's a book by Gullub, I think. Anyway, I have it in a box somewhere. I'll find it eventually. All right. Anyway, so spatial rotation in space-time, and then perhaps more interesting. I think I was in frame there. Let me scooch this up a bit here. So I think of Lorentz transformations as an extension of the concept of rotations to space-time. So of course it has rotations, and it has what I would think of as rotations as a subcase. That's number 1. But the new thing are the boosts, and so these are space-time translations. They're mixings of space and time, and I'll show you on the next page that these really correspond to velocity transformations. So things like this, you got cosh minus cinch cosh, and then of course you can play the game putting them, instead of the first coordinate, you can put them in the second coordinate, or you can put them in the, third coordinate, so to speak, like that. Lambda 1's an x velocity boost, lambda 2 is a y velocity boost, lambda 3 is a z velocity boost, and you can check that these satisfy the condition lambda 1 transpose eta lambda 1 equal to lambda, for whether you have 1, 2, or 3 here. And the determinant, again, is the product of the blocks determinants, which here is the determinant of the cosh cinch block and the identity block, which gives me cosh squared minus cinch squared, which of course is 1, and there it is. Let me, this is, so, when I took a course on special relativity, it was a glorious semester for me. It was the first semester that I had dropped electrical engineering, and I was just a math major. Well, and a physics major. I became a double major in math and physics that semester, and I had 5 classes, and they were all either science or math. It was wonderful. There was no junk in there, no liberal arts to speak of, just pure math and physics. It was a glorious time. And in that course, my special relativity course, which I had out of Wolfgang Rindler's book by Dr. Gould, who was a really nice professor. He was great. Um, he, we mostly, I mean, we didn't see, there were some matrices and things, but most of it was focused on studying the formulas I'm about to show you here, all right? Like, um, and anyway, so, although I, to be honest, don't really recommend Rindler's book. It's a little bit, it's not the best first book. I think they're, anyway, shut up. So the equations for an x velocity boost, so we can talk about going from, say, the unprimed coordinate system to the, say, primed coordinate system, where the relation between the coordinate systems is going to be that the moving coordinate system, the prime coordinate system, relative to the unmoving one, all right? So prime is moving in the relative to the unprime in velocity v, all right? Now, relativity, of course, says that if this is happening, then it's also true that the unprimed is moving with respect to the primed by velocity minus v, right? So it's like one of the fundamental tenets of relativity if you want to go back to the axiomatics that Einstein put down or whatever, but focus my attention here. I'm going to think of the unprimed is static, is sitting there. I think about the primed as moving, all right? And we're gonna set it up so that the observers are coincident at the origin, all right? Meaning that their time zero and spatial coordinates all zero match up, all right? That's the starting point. That's how they're linked. And so then we can look at the equations, right, of the origin of the primed system moving. If it's moving with velocity v in the x direction, then that means 0 equals x prime is this equation, right? But if you look at the equations from the lambda 1, they give you this, all right? Ct prime equal to ct cos phi minus x sinh phi, and x prime is minus ct sinh phi, x cos phi. So what I'm doing is I'm going back, I'm just assuming that we look at this and multiply it by the ct xyz coordinates, right? And I'm trying to explain that in fact this is this coordinate transformation. It may not be readily apparent. I mean, if I just look at this, right, in the abstract and go, what is that? It's not obvious to me that that's an x velocity boost. Let me explain why, all right? So here's why. If you look at x prime equal to 0 relative to this setup, you get minus ct sinh phi plus x cos phi equal to 0, right? And so if I solve that for x over t, right? So x over t, in the sense of we're talking about x over t for the origin of the prime moving system, right? If it's moving with constant velocity, then that, well, if this is not constant, then it's not moving with constant velocity. But lo and behold, when you plug in x, x over t relative to this equation here, like, so take this equation up here, solve for x, we get x is equal to ct sinh phi divided by cos. All right, ct sinh phi divided by cos. And so x over t is in fact the t's cancel, and we see that in fact we get a constant, right? We get c, I guess I can write it here, I still got room. You see we get a constant velocity, it's c tanh phi, right? C tanh phi is that velocity, and so v over c is tanh phi, and so this thought bubble here derives that if we accept these as our transformation equations, right, that means that the primed system has an origin which is moving with constant velocity, c tanh phi, in the unprimed system, all right? And so that's why we call lambda 1, these kind of guys, all right, an x velocity boost, because it corresponds to a constant velocity transformation in the x direction. Now, I haven't said anything about the y and the z directions because there's nothing to say about those at the level of position, right? Y prime is equal to y, and z prime is equal to z, all right? Now, one thing that's missing from Carroll is a discussion of velocity transformations. Perhaps it's in his homework, I don't know, but I will try to give you a homework exercise where you get to explore how velocities transform, right? Like, suppose you've got a particle moving, and you describe the velocity of that particle relative to the prime frame, and then you compare how the velocity of the particle is relative to the unprimed frame. It's not the case that you just have like the y and z velocities are matching for the prime and the unprimed frame. The reason for that, of course, is that velocity is also based on time, and the time, well, the times they are changing here, right? Like t prime and t are not the same. They are related in a somewhat complicated way right here. All right, that said, let me talk a little bit more about this phi. And I don't see that Carroll mentioned this, but maybe I missed it. But phi is typically called the rapidity. All right, the rapidity of the moving frame is phi, where tanh phi is v over c. And also standard nomenclature is beta, is the velocity over c. All right, that's a popular notation. And we may argue, this feels like a homework problem, that if we define phi by tanh phi is v over c, then it follows that gamma is cosh phi, and that gamma beta is sinh phi. Moreover, this gamma is defined to be 1 over the square root of 1 minus beta squared, which is 1 over the square root of 1 minus v squared over c squared. Now, Carroll often puts c equal to 1, so, he might just see this as 1 minus v squared, but, there it is. And finally, just circling back to the lambda 1 equations up here, if I put these back in terms of gamma and beta, I get this, right? Which, if I divide the top equation by c, I get that. And then if I say, you know what, I don't really want to use beta, I want to use velocity and the speed of light, so I have formulas which are understandable to newcomers to this subject and have a minimum of jargon. Well, here you go, right here, right? So here you've got t prime is gamma times t minus xv over c squared, and x prime is equal to gamma times x minus vt. So this right here are the Lorentz transformations for an x velocity boost. And of course, I haven't even written the equations for y prime and z prime, but they're kind of boring. They're just y prime equals to y and z prime equals to z. So here you go, x velocity boost. We can write it in terms of the rapidities, the hyperbolic sine and cosine of the rapidity. Not an accident. There is a tie-in with hyperbolic geometry and the geometry of Minkowski space for sure. So that's why we're seeing this cosh and sinh here. So we can either write the x velocity boost in terms of coshes and sinh, like so, or we could write it in terms of gammas and betas, like so. I actually, for like problems, if I was doing, for example, if I was going to try to transform the field strength, like the electromagnetic field strength, which is we can write in terms of the Faraday tensor in a few lectures, and I wanted to see, like, what do the electromagnetic fields look like in the transformed frame, I would definitely be, I would prefer using gammas and betas as opposed to coshes and cinches, just because they're less writing. But anyway, I don't know, it's kind of silly, but I think in retrospect, about maybe 10% of my effort in the first special relativity course was probably spent trying to understand the interrelation between gamma, beta, and cosh sinh and all this. There's other really interesting things, like the rapidities add. So if you were to define the rapidity of a moving particle in the frame, right? And then, suppose you define the rapidity of a moving particle in a moving frame, all right? And then you asked, well, what's the rapidity of that moving particle relative to an unmoving frame, right? Then it turns out that, like, if you had rapidity phi for the moving frame like I've described here, right? And the moving particle relative to, if the rapidity of the moving particle relative to the moving frame was, say, phi 2, then, get this, the rapidity of the particle moving relative to the static frame would simply be phi 1 plus phi2. When you do your homework problem on velocity addition, you will find out that the way velocities add is not that. It's actually quite ugly. So rapidities add, pretty neat relation. Anyway, let's move on here. So of course you could write down similar formulas for y and z velocity boosts. If I had my copy of Misner, Thorne, and Wheeler handy, I could show you the general formula for a Lorentz transformation in an arbitrary velocity direction. All right, indulge me here. It's going to take me about 30 seconds to get it. All right, I'm back. Now, indulge me further. Let's find it. All right. So I know, there's so many things in this book. But I know that somewhere in here there is the Lorentz transformation relative to an arbitrary velocity. I'm trying to remember where it is. Boost. This might be it right here. Exercise 2.7. Boost in arbitrary direction. So if you do this, whoa! So this will give you the velocity, the boost in the beta. Well, in the n hat, in the n direction. So here n is a unit vector in the direction. N1, N2, N3, I suppose. And so, yeah, if you're a glutton for punishment and you want the formulas for an arbitrary boost, there they are. So that's what Carroll was, if you read Carroll kind of like, you can write them down, but they're hardly interesting. I mean, okay, he's probably right, but I don't know. I think I did that homework problem once upon a time, and it was helpful to me as a newcomer to this wild world of weird matrix things. And also, as a point of personal history, I learned Cauchy cinch for the first time in my special relativity course. So that was the professor was so sad. We come up to him after class. We're like, what are this cosine and sine with an h? And he's like, what? And he's like, didn't you have Cauchy cinch in your calculus? And we're like, no. What are they? And then he was sad because he realized the math people had not done their job, and he had to do it for them. But anyway. All right, so isometries, I'm going to just kind of take a step back here and talk about what is an isometry of R3. And so the last about 10 minutes of this lecture, I'm really begging a question. I know part of the answer to, but not all of, so it's somewhat a setup for one of my many hypothetical homework problems I'm writing for this course. And so here it is. Let me get into it. Now, if we have three-dimensional space, right, we can talk about the Euclidean distance function we know and love. It's the square root of the dot product of the displacement between the 2 points with itself. Or you could say it's the length of the vector which connects the 2 points, right? So this is Euclidean distance function, Euclidean 3 space. Then you can define an isometry of the Euclidean space to be a mapping which preserves the distance, all right? Now, so okay. Now this is, so what I'm following here is roughly Barrett-O'Neill's elementary differential geometry. I forget exactly where, but if you look at my video 22 of 70 in my 2021 differential geometry course, and in particular the lecture I gave on, part of the lecture I gave on 21021, this was a brutal course for me. It meant 4 hours one day, once a week. This is not the way to teach differential geometry. Anyway, that particular video, I break down everything I'm about to show here, okay? So an isometry is a distance-preserving function on the space, all right? So we proved the following theorems, like if you have two isometries, the composite of the isometries is an isometry. A translation, right, is an isometry. Every translation on R3 is an isometry. What else can you prove? If you have a rotation, right, rotation, something of the form Rx equals to Ax, where A is a matrix that has A transpose A equals to I, well then that's an orthogonal transformation, and R is an isometry. All right. And then this one was tough. An isometry fixing 0. All right, so if the isometry maps 0 to 0, well, that's an orthogonal transformation. So you notice that the definition of isometry does not assume linearity. It's just an arbitrary map, yeah? So this theorem, number 4 here, is saying that distance preservation implies both linearity, and more than that, it implies that it's a linear map of this particular form. So it takes me about, let's see here, 15 minutes or so of that video to really prove this, and it's not the easiest thing. It really does require some basis arguments and some things that are, you know, I don't know if I would have found it by myself unless somebody put some money in front of me or something. I don't know. Like, it's pretty tough as things go in this realm. But anyway, that can be proved, and the details are there in that video. And then you can, once you have that, it's easy to prove that every isometry of R3 is the composite of an orthogonal transformation and a translation. So, in particular, there exists an isometry. If you have an isometry, then there exists unique A in R3 and rotation matrix big A, for which f of x equals to ax, and in other words, f of x is an orthogonal transformation, and phi can be written as the composite of the translation and that orthogonal transformation. All right. So 5 is easier. That's really just a relatively simple calculation. It's not trivial, but it's not difficult. 5 is not that hard. And then 6. So the set of isometries of R3 is a group under composition, and in fact we call an isometry of R3 a rigid motion, provided the determinant of the orthogonal piece of its 1. And the reason that it would be called a rigid motion in that case is, like, if you have the determinants not equal to 1, it means that you can tear things inside out. So, like, if you look at the set of symmetries of a cube, the question is, like, do you have to maintain, when you look at symmetries of a cube, are you allowed to turn faces inside out without turning other faces? So, you know, if you don't want to allow that, if you want to keep the inside and the outside out, right? In other words, you're really talking about motions of rigid bodies that you can't rip apart. Then you need to put the determinant 1 condition. That maintains the orientation of things and essentially maintains the relation of different faces relative to each other through that condition, which again means you can't rip it inside out. All right. So all of this just to set up the following question for us, right? This is all standard, not even differential geometry, right? This is classical Euclidean geometry. In fact, if you want to see a masterful presentation of the material I just went over, this stuff here, inside the YouTube videos, I wish I could remember his name. I think he's either Harvard or I think he's a Harvard professor. There's abstract algebra videos where he spends 4 lectures finding all the symmetries of the plane, kind of done in this style. Oh, maybe I'll remember the thing to put a link in the comments. Sorry guys, I just blanking here at the moment. But anyway, that kind of discussion, you know, leads to very interesting abstract algebra. All right, the group of plane symmetries if you specialize to R2 and so forth. But anyway, back on track here. Focused. How about Minkowski space? Can we go through the analog of 1, 2, 3, 4, 5, 6 for Minkowski space, right? So first of all, what's the analog of distance? So R4 paired with this distance. Just look at this, good grief. Sorry. So R4 takes in pairs of points in R4, goes back R4 again, right? So we're going to say the distance from P to Q is the square root of the absolute value of the Minkowski metric acting on the, the increment between P and Q with itself, all right? And of course here G of VW is V transpose A to W, and eta is the Minkowski metric. Maybe I should say matrix. Anyway, so you could call D the pseudo-distance function. I threw a pseudo in there because technically it's not a distance, because you can have the distance between points be 0 and yet those points are not equal. Like if these 2 points fall in what's called the light cone, then if you look at the right part of the light cone, so if like P minus Q is light-like, then this could be 0 even though they're not the same point. One of the things about a distance function, right, is that the distance from P to P is 0 if and only if P is, the difference from P to Q is 0 if and only if P is equal to Q, right? I mean, that's part of distance function. On the other hand, it is symmetric, like the distance from P to Q is the distance from Q to P. But you can work it out. This does not satisfy the triangle inequality either. So pseudo is warranted here. Anyway, that said, and I put the absolute values in so we can deal with time-like and space-like in the same breath, right? You can imagine another discussion where you talked about one distance for space-like and a different distance for time-like, and kind of go that path. But here we just take absolute values so we can talk about them both at once. Anyway, so we say that F is a isometry of Minkowski space if the pseudo-distance from P to Q is the same as the pseudo-distance from F of P to F of Q, right? In other words, F maintains the pseudo-distance between points. And, well, really for all events, because remember we're talking about space-time or time-space if you want to be that guy. So my question is, can we adapt the results 1, 2, 3, 4, 5, and 6 to the Minkowski Minkowski context? Like, I can easily see the analogs should be, right? Like, spatial translations should become space-time translations. What were previously statements about orthogonal transformations should become statements about Lorentz transformations, right? And the group of rigid motions and reflections should become the Poincare group. So these are the analogs I see right off the bat. And I have a suspicion that we can do all this, right? But, I mean, and I'm sure it's been done. But I think this should make an interesting homework. Some of these are really easy, like 1, 2, 3. I think the calculations for 1, 2, and 3 are practically already in the lectures I've shown you. 4 is what I'm interested in. Can we make 4 go through? Can we adapt the arguments in minutes 38 to 53 of that lecture to the context of the current context? Or were the things we did there special? Because I feel like we might have used some theorems about orthogonal basis, and we don't have orthogonal basis now. We've got like eta orthogonal basis, yeah? And so the question is, does the linear algebra transfer over now that we're not dealing with orthogonality? We're dealing with well, we don't really have you could call it eta orthogonal. Maybe I should define that. I can define that. Yeah, that I can define. So what's eta? What do we mean by eta orthogonal? What does it mean for a set of vectors to be eta orthogonal? So if we have, and let me just be a little bit more abstract than we have been up to this point, but suppose you've got R, n paired with eta. And here I mean, well, let's say G. All right, where G is a metric in the slightly more generalized sense, right? It's G is going from Rn across Rn to R again, and we've got G of xy equals G of yx for all xy in Rn, and we also have that the determinant of the matrix of G is not equal to 0. All right, so it's a symmetric, and also it's my bad, G of v comma w equals to v transpose big G w. All right, so this determinant of G I could rewrite as determinant of big G not equal to 0. In other words, big G is the matrix of the metric here. Okay, then you can talk about a set of vectors v1, v2, dot 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 vk. All right, a subset of vectors in Rn is G orthogonal if I think the definition would be G of v I vj was equal to, and here's where I'm going to get into trouble. So if it was just regular orthogonality, right, we would have plus or minus, we'd have just the Kronecker delta ij, right? But here I want to allow for, well, this is too specialized for the general thing, but for our context, it's really just going to be plus or minus delta ij. Right? So like, for a specific example of this, and my apologies for not being more general, so if we had like R4, right, and we looked at E0, E1, E2, E3, right, and G just equal to eta, all right, in the usual minus 1, 1, 1, 1 sense, yeah, then, sorry if I'm off the, I don't think I was off the track here, but then if you look at G of E mu, E nu, right, you're going to get plus or minus delta mu nu, right, and to be more specific, you're going to get, you have G E0 is minus 1, and you have G of EI, no summation intended here, is 1. This is the drag of using summation notation, is you have to say no sum. Alright, so hopefully I wasn't too small. I hope you can see that. But anyway, so my point is that's the fussy part here about number 4, because I think somewhere in there I used an argument about orthogonal basis, but that would be in the traditional Euclidean sense of orthogonal, whereas the analog that we might need here is some theorem about, like, Minkowski orthogonal. But anyway, my thoughts are only partially formed here, so I'll stop there with regard to that homework. But anyway, so I hope that this lecture helps you understand a little bit more about what we're dealing with here in terms of Minkowski space. The Lorentz transformations are the analogs of rotations. We also have space-time translations, which are the analogs of translations. You put all of that together, you've got the Poincare group. The Poincare group have the Lorentz transformations and the space translations and combinations thereof. All right, so Anyway, that's lecture 4. So, thanks, guys.